Alright, in this video we're going to finish up section 4.1 by looking at the last method we use to solve a system of equations, and that is by what we call elimination. In elimination, we either add or subtract the two equations we're giving in a system in order to cancel or eliminate one of the variables, resulting in an equation that only has one variable left, either the x or the y, which is very easy to solve then once it's down to one variable. So in order to do this, we take a look at the equations we're given, and we determine right off the bat if we can add or subtract these two equations to cancel either the x or y terms. And if that's the case, we want to go ahead and approach the problem that way. Looking at our first example here, we have the system 2x plus 3y equals negative 6 and 4x minus 3y equals 6. So again, the first question we ask ourselves when we're trying to use the elimination method: if we were to add or subtract these two equations, would either the x terms or the y terms cancel each other out? Looking at our y terms, we have opposites, 3y and minus 3y. When we have terms like that, if we were to add equations, that would cancel out the y terms because they are opposites. So, writing that in here, y terms are opposites. So, excuse me. So we add. Okay, in order to cancel or eliminate them, we add the two equations. So I'm going to rewrite the equations over here. 2x plus 3y equals negative 6. 4x minus 3y equals 6. And again, we are adding these two equations in order to cancel the y terms. So adding them up, we just look at everything vertically in columns. Adding 2x plus 4x is going to give us 6x. The 3y plus a negative 3y, those cancel. That would give us 0. And then 6 plus, or negative 6 plus 6 also would give us 0. But we do need to write something on that side of the equation, so we do have to put in a 0. So we're left with the equation 6x equals 0, an equation that's only in one variable, and an equation that's very easy to solve for x. We just divide by the coefficient of 6 on both sides, and we get that x has to equal 0. Okay. So remember, in a system, we're trying to find an ordered pair that is a solution to both of these two equations. Right now we found half of that answer. We found the x-coordinate of our ordered pair. We now need to come back and use that x value to find the associated y value. So we can use either of our first two equations from this original system, plugging in 0 into that one of those two equations to find out what our associated y coordinate has to be. So here we can I'm just going to take the first equation, 2x plus 3y equals negative 6. Replacing the x with a 0, we get 2 times 0 plus 3y equals negative 6. The 2 times 0 kind of zeroes out the x term, and we're just solving an equation for 3y then. So 3y equals negative 6. Solving that equation for y, we would divide on both sides by the coefficient 3, and we get y equals negative 2. So our actual solution to the system that we started with is the ordered pair 0, negative 2. Okay. That's the one-ordered pair. That would work for the first equation and for the second equation. Flipping to the next page of the notes, let's look at two more examples of solving a system by elimination. And then we will be done with this section. So, next example, we have x plus 3y equals 8 and 2x minus 5y equals negative 17. So looking at these two equations, we want to use the same approach and try to determine if we were to add or subtract these two equations, which variable, either the x terms or y terms, would cancel each other out. However, this one's going to be a little different, because if we were to add our x terms here, we would end up getting x plus 2x would be 3x. 3y plus negative 5y would give us a negative 2y. That wouldn't cancel them. Even if we subtracted, 1x minus 2x would give us a negative x. 3y minus a negative 5y would give us a positive 8y. So that's actually not going to work right off the bat like the other one did. Instead, we're going to have to manipulate one of the equations first, and then to get it into a form where we can add or subtract the two equations to cancel out x or y. So we have some options here. We can make a decision, what we think would maybe be the easiest. A lot of times when you have a coefficient or have a variable without a coefficient, we can make this x here have whatever coefficient we want. We can stick whatever number we want in front of this x, as long as whatever we multiply by to get that out front, we multiply everything in the equation by that value. So we could make these two x's match up so that we could subtract the two equations, or we could even make this x have a coefficient of negative 2x and add the equations to cancel them out. Either way. So I think we're going to do that. Let's try it that way. We're going to take this equation and multiply everything in that top equation by 2. As long as we multiply on both sides by 2, then it's an okay move to make. So we're going to multiply by 2 to get the same x term. Okay. So when we do that, I'm going to rewrite the system over here. 2 times x will give us our 2x. 2 times 3y gives us 6y. 2 times 8 gives us 16. Bottom equation, we'll just rewrite that. 2x minus 5y equals negative 17. Alright. Now the way I've had you set this one up is so that the x's essentially match each other, but that means we can't add these two equations to cancel out the x terms. We'd have to subtract, because 2x plus 2x would give us 4x. However, if we subtract 2x minus 2x, that would cancel it out and give us 0. So if we have the x terms are exactly the same, we have to subtract the two equations. Okay. So let's line these up, subtracting now vertically. The 2x minus 2x cancels each other out. That gives us a 0 for our x terms. Here's where you do have to be careful though. We're doing 6y and we're subtracting a negative 5y essentially, because we already had a minus 5y here. And what that actually is going to give us is an 11y. I'll re-explain that here in a second. Same thing happens over here. We have a 16 and we're subtracting a negative 17. So that's actually the same as adding. That's going to end up giving us a 2033. Okay. So here off to the side, kind of show you why that is the case. We had 6y and we were subtracting a negative 5y. And when you subtract a negative, it's the same as adding. That's why we ended up getting 11y there. And we did the 16 minus the negative 17. Again, that's the double negative, cancels each other out. It's as if we were adding the two to give us 33 there. That's one of the reasons. I don't necessarily like to do subtracting. You do have to be careful with the signs when you have negatives in the bottom equation when you are subtracting. So if you would have rather multiplied everything by a -2 to make this a -2x up here, and then you could have added the equations, that would have worked as well. You still would have to be careful with your signs here and here when you're adding two negatives and adding two negatives. So I guess it's however comfortable you feel with negatives and adding and subtracting. To finish this off now, solving it for y, divide by the coefficient of y, 11, and we end up getting y equals 3 when those cancel. 33 divided by 11 gives us that. We then want to plug that value into either of the two original equations and solve for x. Whichever one would be easier, you could choose. Last example, there really wasn't one. This one, I would say the top equation would be easier. X plus 3y equals 8 was the original equation. Replacing the y with a 3, we get x plus 3 times 3 equals 8. And multiplying that out, we get x plus 9 equals 8. Subtracting 9 from both sides, we would get x equals -1. So now we have our ordered pair. That's our solution. X coordinate is -1, y coordinate is +3. Once again, that is the one ordered pair, x and y. Sorry, this needs to be in parentheses because it is an ordered pair. That if we plugged in the x value, -1 for x and 3 for y, it would make sense here and give us 8. If we plugged in -1 here for x and 3 in here for y, it would give us -17. And that is the one value that will do that. Okay. So let's finish up one more example here to finish off the section. So here we have the system 2x minus y equals 3 and 6x minus 3y equals 9. Once again, we can't add or subtract right off the bat. Our x's wouldn't cancel if we added them. That would give us 8x if we added them. Subtracting would give us a -4x. Adding our y terms would give us a -4y. Subtracting them would actually give us a -1 minus -3, which would be -1 plus 3. It would give us a +2y. Either way, it's not canceling either the x's or the y's out if we add or subtract. So we want to manipulate these equations. Again, usually when you do that, look for the variable that doesn't have a coefficient, has technically a coefficient of 1. So with the y, we can multiply by 3 to make these two kind of match each other. All right. So if we take this and multiply the top equation by 3, well, let's bring our system down here. We end up getting 6x minus 3y equals 9. And then on the bottom equation, we already had 6x minus 3y equals 9. We see we get the same exact equation written twice, which technically means, remember from the graphing situation, we would be graphing the same line. They'd be right on top of each other. So we have what we call infinite solution, or infinite solutions. So same equations. The conclusion here is that we have infinite solutions. And even if you were to come over and try to continue doing a method that we were doing above on the last two examples, and we try to subtract, okay, we have 6x and 6x, those cancel each other out when we subtract. We have a -3y and another -3y, they're the same value, so we subtract to cancel, those will end up canceling as well. 9 minus 9, those will cancel. We end up getting a situation that gives us 0 equals 0 on both sides. And when we solve equations, when we get a true statement like this, you know, not x equaling a number, but just a number equaling a number that's clearly true, that's the we make the conclusion we have infinite solutions. All right, and that's everything for 4.1. We looked at all our three different ways that we solve systems.